We will do the second part of our discussion about transactions. So as you may remember, or those with good memory may remember that last time we talked about two of the acid properties. We talked about atomicity and durability, which is what recovery techniques take care of. And we learned 4 basic recovery strategies, along with a possible add-on to those. The add-on was the checkpointing operation, and the 4 strategies were composed by choosing whether we will need to perform redo or undo operations after a crash or after a failure. I mean, those strategies define whether we need to do the one or the other or both or none of them. Redo and undo, right, on transactions. I mean, whether there will be transactions that we will have to just go through once again by reading the log file to make sure that all their effects are really recorded, or transactions that we have to just cancel based on what has been done on the log, or transactions, or whether the strategy that we follow is designed in such a way so that we will never have to perform those operations. And that way, we ensure atomicity and durability. Today, we will talk about the 2 other components of the ACID strategy, which are consistency and isolation. So where consistency means that the performance of multiple concurrent transactions brings the system from one consistent state to another. In other words, it doesn't create errors. It doesn't bring the system to an erroneous state. And that's a need that arises when you have multiple transactions done at the same time. So that's why it's about concurrency. And the isolation part means that it should all look as if each transaction was carried out alone, even though, in fact, they are operating along with others. And in this area, there is one important concept we have to learn. That's the concept of serializability. So there are some schedules. So a schedule is also an important concept. So a schedule is just a plan of executing some transactions in an interleaved manner. So one operation of one transaction takes place, then another one, and they may be combined with each other in some way, or you may try to combine them in some way, so that eventually all of them carry through. But of course, you may encounter some problems as you try to do that. And a way to describe the problems that you encounter is that perhaps the schedule that you design is not a good one because it's not serializable. Or if it's a good one, it means that it will be serializable. So as you understand from the term, serializability is about the ability to make it look as if they happen one after the other, although in fact they do not, but it should be equivalent to that. And in that sense, when you have serializability, you ensure isolation and you ensure consistency, since they don't interfere with each other, or they perform in a way that is equivalent to a non-interfering way. So, and after we understand those concepts, what is a schedule and what is a serializable schedule, we will learn the 2-phase locking protocol, which is a technique or a set of rules that we follow, and when we follow them, they guarantee that whatever we do is serializable. So we don't need to worry about serializability once we follow this protocol. And as a side effect of this discussion, as a side effect of our discussion about 2-phase locking, you will effectively become ready to answer the question in the final assignment that has to do with concurrency control, because it asks you, as you may have noticed, it asks you to do something according to this 2-phase locking protocol. But then there is something more we will learn about. So 2-phase locking is just one out of many protocols that we may follow. And so it's good for us to realize that things are wider than that. So we will also talk about another technique called timestamping. And that's an interesting thing to look, because we will realize that there are some things that you do well with 2-phase locking, some other transactions, interleaved transactions that perform well or become serializable and executable thanks to two-phase locking. But some other ones can benefit from timestamping, so that those two protocols perform well in different situations. And we will see how that happens. That will be the end of the discussion. So to start with this, we are talking about the idea of concurrency. So the idea that there are several transactions that operate or get performed together. Why? Because we have a system that allows many users to access it. So there is a distributed setting. Many people have access to the same database from different positions, from different terminals. And you want all of them to experience an efficient performance. So you want to allow them to do things at the same time to some extent, to the extent that doing things at the same time does not create bad states of your database. And that's a good thing. So we want to push things to be as concurrent as possible. Right? So there is an easy solution. We can always let only one user act at a time, and then we have all the correctness we need, but then we don't have the users experiencing efficiency because some of them have to wait. So we are trying to bring things together as much as we can. And to do that, we have the system that allows this to happen has to design a schedule, which is a sequence of operation from several transactions, and has to figure out whether it is safe to execute a schedule as it is in a certain form, or perhaps to make some change, to just execute a few things in a different order so that it will still be okay. So that's what those protocols have to decide. Is a schedule okay to be executed? Should I change it? And the system does those decisions on the fly. So when those protocols are running, they have a way to determine whether a schedule is acceptable or whether it can be slightly changed and still be acceptable. But so in our discussion, we will just be looking at schedules. So we'll be looking at operations or commands from several transactions put together in some order. And we will be discussing whether they are safe or not, or whether they agree with one protocol. Right, so that's what. So we will be doing actually the job that the system does internally, and we will be discussing about how we can make a decision. And so those transactions, we talk about transactions that perform some operations. What operations do we worry about? Well, as you would expect, we care about operations that interact with the database on the disk, so read and write operations. So there is a read operation in which a database item Q is stored at some local variable. Those are similar to those we discussed last time in the context of recovery. And there are write operations where a database item Q is stored or written to a local variable. And as soon as something is written to a local variable, as you remember from our recovery discussion, it is as if it is written on the disk. Right? I mean, the recovery operation will take care that even if there is a crash, whatever has been written or read will eventually either be fully on the disk, so I mean, all the operations of a transaction will be reflected on the disk, or none of them will be reflected. That's last time's discussion. Today, we consider that all of this is fine. We don't worry about failures, and only we care about concurrency. What happens when several transactions do such operations at the same time? So we don't care. As you understand, we don't worry about what happens in the CPU, so what computations they do, because those have no effect on writing data. So they are, of course, part of a transaction, but they don't create conflicts. And of course, a transaction, as we learned last time, arrives at a point of commit, or it can roll back. I mean, that is the same as what we called undo. So to make all this concrete, here is what I mean. Here is an example of a schedule. So here on the right-hand side, you see a schedule called S0, and actually there are two transactions that perform kind of concurrently. As you can see, they are not so much concurrent. I mean, you have transaction T2 taking place early, very early, I mean, in first priority. And then you have transaction number 1, and this is 1. So that's one possible serial sequence. You see 2 comes first, followed by 1. And both of them operate on a database that has 2 items, x and y. We want those 2 values to be equal. I mean, we follow this rule that every transaction that operates on those 2 items should always keep them equal. I mean, that's an easy rule to invent so that we see how things work and whether something was done that violated this rule or not. So transaction 1 just increases both by 1, and transaction 2 multiplies both by 1. And of course, both of them store new values. So if we do everything correctly, those 2 values should remain equal. You know, any correct schedule of executing those transactions, any serializable schedule, should preserve that property. Well, and indeed, as you see, so if at the beginning they get both x and y get the value of 10, and we invent this serial schedule, I mean, it's quite obvious, right? One transaction done completely, followed by another. Then what do you get? First, you have both values doubled because of transaction 2, and then you have both values increased by 1. So of course, 2 times 10 plus 1 equals 21. So of course they remain equal. So as long as you, of course, since we separated the transaction. So in this case, things are quite straightforward. We have a serializable schedule. But check out this one. So what did we do here? So here we have created a schedule that is a bit more, it has a bit more of concurrency. So we really interleaved the 2 transactions. And so a bit of T1 takes place first. Then the whole of T2 gets executed. And then we get the rest of transaction 1. So that's also a concurrent schedule. But unfortunately, it doesn't preserve the property that we defined, which was this easy property. So we expect that x and y will always be equal. And this doesn't happen, right? So look, first you increase x, then you double both x and y, right? So x became 22, but y just became 20, because both of them were doubled. And then you do the rest of transaction 1 that adds 1 to y. So they get the value, x becomes 22 and y becomes 21. So clearly what we got here is not a serializable execution. Okay, so it is not equivalent. So of course that is some kind of schedule, but it's not equivalent to a serial schedule. So we don't like it. I mean, it doesn't look like as if they were done sequentially. To be serializable, it means that it should be equivalent to either doing T1 first followed by T2 or vice versa. Right, so that's what we are concerned about. We would like to avoid concurrent executions like this one, which are not serializable. And we would like to have transactions interleaved in other ways, in legal ways, which are equivalent to a serializable execution. Right, so in this case, this one should not be allowed. The system should eventually abort those operations. Okay, it should discover that this schedule doesn't work as a serializable one and leave it. But to get there, okay, so we know the rule. We know what we want. We want serializability. How to detect it? How do we know that something is serializable or not? Well, there is an easy way to decide that. So 2 transactions called I and j are in conflict with each other if there is an item called x that is accessed by both of them, and at least one of them does a write operation. I mean, if both of them read x, you don't care. They can read it as many times as they wish. They will never, they cannot ever be in conflict. But if at least one of them writes this item and the other reads the item, then they have to worry about each other. I mean, they have to worry, will I read the value after you write it, or will I read it before you write it? So they have to know the answer to this question, and the system has to know the answer to this question. Okay, so in that case, there is a conflict between them, but a conflict by itself is not a bad thing, as long as we take care of it. So as soon as we know there is a conflict, we have to be aware of what order of execution we would like to achieve. So we would like to achieve a concurrent execution of transactions as if they were in some specific order. It's not a bad idea to be in conflict. The bad thing is to be in conflict and to not know what is really going on, to not know whether it's equivalent to Ti coming first or Tj coming first. So if two transactions, so as soon as such two transactions that are in conflict exist, if they are in conflict, we have to take care of their order. If they are not in conflict, we can swap them and we don't mind. Right? And in that case, we say that any order of execution is equivalent in the face of conflict. But then, if we can define an order of execution such that we absorb the conflict, so we make them just equivalent to some kind of concurrent execution, then we say that they are conflict serializable. So we produce a schedule that is conflict equivalent to a serial schedule. So in other words, we achieve what we are saying when we say that we want to have isolation. We want everything to appear as if the transactions were executed one after the other, even though they don't. I mean, even though in fact there is some concurrency, you should say, I don't mind about this concurrency because everything that happens is the same as if T1 was done first and T2 was done second. So here is an example of that. And now is a chance for you to decide. So we have those two transactions, T3 and T4, in a certain schedule. And the schedule is as you see on the right part of the picture. And the question for you is the following. Is this mixed schedule? So this schedule, as you see, has the transactions interleaved. You know, a bit of the one followed by a bit of the other and so on. But of course, by just reading one column, you see what one transaction is supposed to do. And here you see what the other is supposed to do. And so you can realize what happens if one is done first, followed by the other, or vice versa. They are the same transaction as before. One has to increase values of x and y, and the other has to double them. And we follow this order. So the question is this thing now equivalent to a performing transaction 3 followed by 4? Or is it equivalent to 4 followed by 3? Or is it equivalent to both these orders, so that order doesn't matter? Or none of that? So here is the question for you. So, okay, I leave that slide so that you get the number. So that's the number we are working with. And now that you know the number, we go here. Yes? Sorry? The code. Here you are. Okay, here is the code, and here are, okay, some people have voted. Okay, that is let's go back. Okay, so we got a lot of opinions. I mean, we have a clear majority. And so the majority says it's none of that. And some people voted for other things. So let's see what is really going on. I mean, yeah, so it's none of those, but still there is something else that is, another interesting thing is going on, and some people, I think, may be influenced by that other thing. So if you look at it, you will see that, yeah, it's not equivalent to doing both of those, one followed by the other, but actually, look at transaction 4. It reads X before it is affected by 3. It does what it does, and then it writes X. It's the second one to write X. And it reads it before T3 has done anything. Also, when we come to item Y, T4 will read Y before transaction 3 has done anything, and it's also the second to write Y. In other words, transaction 4 completely carries the day here. It behaves as if it's the only one that exists. I mean, the whole schedule behaves as if only T4 exists, and transaction 3 does not make its presence visible at all. Yeah, so it's not equivalent to doing 3 followed by 4. It's not equivalent to 4 followed by 3. It's actually equivalent to doing just transaction 4. So and that's a problem, of course. That's not what we want. We wanted to have both of them. I mean, we wanted to increase the items and double them. Either first increasing and then doubling would be one good, one serializable schedule. It's a serial schedule, so if that schedule is equivalent to that, it would be serializable. And vice versa would also be acceptable as serializable. But here we don't have serializability. Here we have T4 wins everything. Right, so some people may have noticed that thing, and that's why they voted for another option. So since they observe that T4 behaves as if it is isolated, yeah, it can mislead you. So you see, we have isolation here, but just for T4. T4 behaves as if there is nobody else in the world, but for T3, things are not so bright. We lost it completely. Its effects are completely vanished. So we don't like that. That's not a serializable schedule. We don't want one transaction to be completely wiped off by the other. We want both of them to survive in a way, either by being first and second or in the other order. So that was the idea. And then now that we know that, let's become more specific on what we mean by conflicts. So we already said that two transactions are in conflict if they operate on the same item and at least one of them writes on it. So here are the particular cases. If one reads and the other writes, if one writes and the other reads, they are in conflict. If that happens in reverse, again, they are in conflict. Right? And we must have some sequence. If both of them write on it, then even more, for sure, they're clearly in conflict. And again, we have to know, we have to specify which one is the last to write. Okay, and we want to be in a schedule. But if both of them read an item, then we don't care, right? It doesn't matter which one reads it first and which second, since the value remains unchanged, and they're just both going to read the same value, assuming these are the only transactions in the world, right? In a closed world of those two. So yeah, this is just specifying further what we previously said. And then with this repository of concepts, with this armament of concepts, now we can define another interesting thing. We can define a conflict graph. So a graph, as you know, is a mathematical model with edges and nodes, or vertices and edges. And here we will just use one vertex for each transaction. So T1 is represented by that thing, T2 is represented by the other thing. And we use those graphs to represent how much two transactions are in conflict. So whenever there is a conflict between, in this graph, T1 and T2 because of an item, we create an edge, like this one, and we put a label of that item on the edge. So we put an edge from Ti to Tj. If Ti conflicts with tj on x, where to conflict means we are accessing the same item and one of us writes on it. And we know who has to be, we have an idea that the one has to be first and the other has to be second as far as this item goes. So as far as item x is concerned, we know that, look at this, T1 writes on x and T2 reads it. And the way this schedule is designed, it is T1 that comes first. So in item x, we want T1 to be the first one, followed by T2. And then we create the edge for Ty. And in that case, this schedule says that transaction 2 has to write on it, and after that, transaction 1 has to read it. Okay, we express this sequence in the graph. We say, as far as y is concerned, T2, transaction 2 is coming first, and as the edge indicates, it's followed by transaction 1. So this graph is a useful concept because every conflict among two transactions is expressed by an edge. And then we can visualize all these conflicts. And as we said before, a conflict by itself is not a bad idea, just to exist. If, now we can express with a graph what's the condition that should be satisfied. If all the conflicts point in the same direction, so if for all conflict edges T1 is followed by T2, then we have no problem. They're compatible with each other. All of them require that T1 is performed first and T2 is performed second. I mean, all of them require that based on whatever schedule we have come up with. So if we observe that this happens, it means that the whole thing is the same as if transaction 1 is first and transaction 2 is second. Right? If that was the case. But here, as you can see, that's not the case. Right? The two edges do not point in the same direction. Look, one edge goes from T1 to T2 and the other goes in reverse. And how do you say that? So in graph theory, or you don't even have to know graph theory, you just look at this. That thing is a cycle, right? I mean, look, you start from T1, you go there, and then you can come. If you follow the directions of those edges, you see they have arrows on them. The edges make a cycle. When you have a cycle in the conflict graph, you know you have a problem. If your conflict graph has no cycle, it has no problem. So a schedule that creates a conflict graph that is acyclic or without cycles is a good one, is a serializable schedule. If it has a cycle in the conflict graph, it has a problem. So that's the rule. Given that now you know the rule, let's do another question. So here is a larger schedule. So here we have a list of 5 transactions. Actually, one of them, you see, is just standing there by itself. All of those operate on some items, X, Y, Z, V, and W. And I already did the work for you, so I went through this schedule, and here I have built the graph, the conflict graph for this schedule. For example, I have an edge from 10 to 11 because of item Y. Why did I do that? Because there is transaction 10 that reads Y very early, and transaction 11 writes on Y a bit later. So there is an edge from 10 to 11 with label Y. There is another edge from 11 to 13. Why? Because 13 writes also on item Y a bit later, after 11. You see, time goes from top to bottom. And every other edge indicates that kind of relationship. Look at Z, for example. As far as Z goes, you have 10 followed by 12 followed by 13. Indeed. 10 reads Z, 12 writes on Z, 13 also writes on Z. That's why you have those Z edges. And another Z edge from 10, directly to 13, of course, and also a Y edge from 10 to 13. And then there are some reads also. You see, there are some items that don't appear in conflict edges, like V and W, because V is just doesn't create any conflict, and W is just touched by this one. So that's the conflict graph that we got. And then the question is this a fine conflict graph or does it have a problem? And you have some options. Maybe the problem is that 14 is just standing there by itself, or something goes wrong among 11 and 10, or the 10 and 12. Yeah, so you can vote on that one again. Okay, look at it again. Okay, it looks like we have a full house on this one, uniform agreement. So indeed, yeah, you are very right. This schedule has no cycles, because, so as you see, yeah, it looks like there is a cyclical pattern, but if you follow the arrows, the pattern is not really cyclical, so you can't take a turn. So you just go, everything goes in a direction from upper left to down right. So clearly, everything is fine, and everything looks as if T10 is followed by T13, and the other two happen at some time between. I mean, both 11 and 12 happen between 10 and 13, and you don't care which of those two happens first, because those two are not in conflict with each other. That's what concurrency is all about, after all. We would like to have things happening without worrying which happens first when they don't conflict. Yeah, and T14 is just standing there alone, and again, it doesn't bother anyone because it has no conflicts. So everything is great here. You are right. Okay, we got some extra votes. So somebody said T11 should precede T10. Well, you don't need T11 to precede T10. It's fine coming after 10, because the only worry you have is that it's going to write on item Y, which transaction 10 is reading. And it's reading it before it's written. So as far as Y goes, as far as item Y is concerned, transaction 10 is the one that comes first. Can we assume that it really comes first on everything? Well, indeed, there is nothing else. There is no other conflict that they have. So even though transaction 10 does a lot of work much later, we don't mind, because we could just also assume it was done early, and everything is equivalent. So everything that happens here is just the same as if the whole of transaction 10 happens first. Right? So that's why, that's not a problem. It shouldn't, T11 shouldn't precede 10. So that's the situation. And then, so in effect, we know how to test serializability. As you very well applied, a schedule is serializable, or more precise, conflict serializable, if the conflict graph it creates or it induces is acyclic, which means it has no cycles. And then just a topological sorting, what does that mean? Well, if you just take the transactions in the order that they appear to come, you know that you have to do 10 first, then any of those two in any order, you don't mind, and 13 last, and again, 14 can also be at any place. So that's what we mean by topological sorting. Any kind of sorting that obeys the acyclic conflict graph is fine. If the conflict graph has a cycle, we know that this schedule is not good. We have to change the schedule to just change the order of some operation we want to perform so that eventually we can find some kind of order of execution or schedule which is equivalent to a sequential one or a serial one. And the question is, how can we do that? Okay, so if the graph is acyclic, we are great, everything is great. But if we don't know, what can we do? So we have a schedule is given, or we try to create our own schedule which looks like it's efficient. Then, okay, if we follow our knowledge, we can just go ahead and build a graph, test the graph for serializability, so check if it has any cycle. And if it has, start from scratch again. Or, try to create a new schedule. So that would be very time-consuming. I mean, we don't... This approach, this strategy, has no suggestion on how to generate a good schedule. It just has a suggestion on how to test your schedule. So you have no guidance on what to do. Right, I know you don't like that. You don't like situations with no guidance. You like situations with guidance, like in the assignment. So strategy one is bad. Just keep trying until you get it right. So we would like to invent something else. So how about the other strategy? Let's create a protocol which the system will have to follow. And this protocol by itself guarantees that any schedule we create when we follow it is a serializable schedule. So now we have a guidance. We don't have to just make a schedule, check it, and then go back and try again. We will just always follow our protocol. So as we create a schedule, when we see something that violates our protocol, we change it. We try to fix it. Of course, we need a guidance also on this one. We have to know how to change our schedule, but at least we know the idea, we know something that we have to obey, which is not just the idea that a graph out there must be acyclic. It will be something much more well-defined and much more specific that this protocol will say. So let's go to define such a protocol then. So what kind of protocols should we create? Well, here is a suggestion. Let's make things in such a way so that some transactions will be allowed to lock an item. So a transaction is allowed to say, this item here, I'm going to work with it. I want to lock it, which means nobody else can touch it except me. Or actually, what I just said is what we call the exclusive lock. There is another lock that we can request. You just say, there is this item. I'm going to be reading on it, or reading it. And so I just want to inform everybody else that I am going to be reading this item, and I take what we call a shared lock, where shared means I lock it because I'm going to read it, but anybody else who reads it can also lock it just like me, and all of us share this item, and we are happy as long as nobody is going to write. So we can all, many transactions can have a shared lock because all of them just read. But as soon as there is one transaction who has to write on an item, it's going to acquire or request and obtain an exclusive lock, which means that I read this, everybody else is out. I don't want to be bothered by anyone. As long as I read and write on this item, I'm going to be the only one touching it. If you have seen a very old movie with a Highlander in Scotland, you may remember this phrase, memorable phrase from an old movie, there can be only one. So that's the idea of an exclusive lock. There can be no transactions, several transactions, writing on an item at the same time. I lock it first, I get an exclusive lock. When I'm done, I release the lock. Then somebody else can lock it. They can also write on it, and it goes on this way. So at most one can have it, whereas the shared lock, as the name suggests, can be shared. So many transactions can just keep reading the same item. But then you will ask, why do we need the shared locks? Okay, the exclusive locks have the purpose that we inform the world that we are writing on this item. So we need an exclusive lock to send this message. What about the shared locks? If they can coexist, okay, what's the point of having them? Well, you need to have the shared lock so other people know that they cannot get an exclusive lock. If nobody has a shared lock, I can get an exclusive lock because nobody is reading this item. If a community of people are happily sharing their shared lock, or a community of transactions, I know I have to wait for them to get the exclusive lock I want to get. Or if I want to get a shared lock, I just join them and I become one of the readers. So that's the idea. That's how things behave with those tools we invent. Exclusive and shared locks. And of course, we cannot just obtain those locks. Sometimes we need to release them, right? We have to inform others, okay, go ahead, now it's your turn, I'm not writing on this anymore, or I'm not doing anything. So we can have those unlock operations. And those operations are performed on items like those Q, and we write them like LX means exclusive lock, LS means shared lock, UN means unlock. And for even shorter, we can just drop that. We can just write X for exclusive lock, S for shared, and U for unlocking. So that's the principle of locking. Let's see an example of that. I mean, let's take a transaction, the way it is written, and try to write it in some convenient shorthand notation, with all the locks it should request and get. Okay, here a transaction is called T7, and it has to read item B, subtract 50 from it, then write it. And then it also reads item A, and it just displays the sum of A and B. So the operations it does are in black. And now in this schedule, and also you can see them in black here in this box, okay, for short. R stands for reading, W stands for writing, the subscript there, 7, is the transaction's number, and what you have in parentheses is the item that is read or written. And some semicolons just separate operations. So you see, we are following this syntax now to make things convenient and short. So this syntax here in black starts for all those black things. And you see that I have inserted all the locks that you need to get. And the locks are in red color. I mean, the exclusive locks are in red color, and okay, and a shared lock is in blue because it's not so prohibitive as the exclusive one. So you see that at the beginning, this transaction is going to read B, but we also know, or the scheduler knows, that it's going to be writing on B. So it requests an exclusive lock on this item. There is also an approach that first you can request a shared lock, and then you can request to upgrade it to exclusive. But now, for simplicity, let's keep things clear. You know you're going to both read and write something. Okay, you want an exclusive lock. There, you ask for it. So here it's also written in shorthand notation, exclusive lock by 7 on B. After it has done all the work, it releases that. Okay? And then it says that it's going to read A without ever writing on it, so the only thing it needs about A is a shared lock. So there it requests it in blue color, and after it has done that reading as well, it unlocks A as well. Okay, so this is a transaction with some locks introduced. Of course, it's alone, so there wouldn't be a problem in any case. It just got what it wanted, it released them, everything is fine. The interesting question for us is how should we arrange things when many transactions operate together? What rule should we impose on them on the way they get and they release their locks, so that by following those rules, they just produce a serializable schedule? So that's the interesting question. And so the rules that we invent should prevent problems. So let me show you a problem. So now 7 is not alone anymore. Now I introduced a peer transaction. There is 8 running side by side with 7. Actually, it runs just in the middle. So at some point inside transaction 7, here is a whole operation of 8 running. Okay. And you would like the effect of these two transactions to be serializable. Well, actually, if you look at it, it's a situation similar to what we had before. Well, in fact, things here are not that good. So transaction 8 reads both A and B. as you see. It's just a transaction that has to read those two values and display their sum. Well, it reads the one after 7 operated on it, and it reads the other before 7 operates on it. So clearly, the sum it prints out is not the same as it would be if it ran totally before or totally after. It's none of that. It's because it is just completely in the middle, and in fact, it comes after the writing on B and before the writing on A. Okay, so clearly that is not a good schedule. But then we have all the locks. I mean, look, 7 takes the lock that it wants, it releases it. This guy also takes its locks. So as far as locks are concerned, everything is great. So how can we describe our problem? I mean, how can we define something that is done in terms of locks which describes our problem? Well, if you look at it, you will see that here the idea is that both of them operate on 2 items. The one of them locks B and then unlocks it. And then, after it has unlocked B, it locks something else. That's what creates an inconsistency here. You see, I mean, the fact that transaction 7 is allowed to unlock something, and then the whole of 8 comes through, it passes through and does everything, and then 7 says, oh, I forgot to tell you, there is something else I want to lock as well, because I'm also going to operate on A. The fact that it has unlocked B and then it locks A is a bad thing. If we prohibit that from happening, so if we prohibit 7 from unlocking B before taking another lock that it needs, so if we impose a rule that says, you are not going to unlock any item before you take another lock. If we have such a rule, this wouldn't happen. I mean, those two would not be possible to be executed together. I mean, if 7 doesn't unlock B, 8 cannot lock it. Here, 8 wants to get a shared lock on B, it wouldn't be possible. So, you see, we can impose a rule that would prevent such inconsistencies. So that's one inspiration. Let's see another inspiration. Again, here we have 2 transactions. This time they're called 9 and 10. And now, okay, we have not just put the 1 in the middle. We just have both of them in a quite balanced way. They run together, one with the other. And what they really want to do is that 9 wants to, again, it reads B and subtracts its value. And then it's going to write on B. And eventually, it's going to want to lock A as well. On the other hand, 10 wants to lock A because it reads it. It wants to get a shared lock. And then it also wants to get a lock on B. I mean, look at those underlined lines is what they want to do at the moment. And as you see here, they have not done unlocks. So what happens then to them? Transaction 9 wants to get a lock on item A, so it's waiting for 10 to release it. 10 has a lock on A. It's a shared lock, but it doesn't matter. 9 wants to get an exclusive lock, so it has to wait for the shared lock taken by 10 to be released. And in reverse, transaction 10 wants to get a shared lock on B because it has to read it at some point, or it wants to work on it later. And it has to wait for that to be released by transaction 9. So both of them wait for each other. 9 waits for 10, 10 waits for 9, and they're just going to stay there forever. So that's another problem we want to avoid. Okay, and that problem is called deadlock. So there is a way to follow a rule that avoids this problem, and it's called two-phase locking, and I will tell you about it after a break.